Hello, this video is about the definite integral. So we're going to connect the idea of approximating the area underneath the curve from the last lesson to some new notation and some easier ways of finding the exact area underneath the curve. So first major thing to talk about here, we're going to talk about area, right, to review this basic idea, but we're going to introduce a new concept, and this is called net area. So this is very much the same idea as just talking about the area underneath the curve. It's this idea of the net area that's brand new. So we'll just talk about this. So you can look at a curve like this, something that dips underneath the x-axis but also goes above the x-axis. And so in the conventional sense, we can think about the bounded area, the area that's enclosed here and the area there. And you can see in this diagram we're estimating the area underneath the curve by putting in some rectangles there. So if you think about the old way that we talked about this, right, in the previous lesson, the area of a rectangle we calculate by looking at the height, and we multiply by the width. So you can see the width here will be constant for every single one of these rectangles, but the height here is the peculiar feature, because in the previous lesson we talked about the height as being the y value of the function. So we often wrote it this way, perhaps f evaluated at some point, f of c, right? And then the width here would be some constant value. We might call this delta x, right? Just a change in x. So this definition of area makes perfect sense when we talk about this portion of the curve where the y value of the function is a positive output. But you can see that the definition is a little bit different when the value, right, the y value of the function goes negative, because then that means the height here is actually negative. So this is the reason for calling this the net area, because we're really saying that when you calculate this area underneath the curve, we have to use this word carefully. Right? When we talk about area, we're not talking about area in the conventional sense, and this is why we call it the net area. So when you look at this diagram, we would say that this area that's above the x-axis would contribute in a positive sense, right, just as we would expect, but then the area underneath the x-axis, this would contribute in a negative sense. So really we're saying that area can calculate to something that is negative or positive, hence we use the adjective net. So this is telling us that the areas can contribute in multiple ways, both positive and negative. So the big thing that we're going to talk about here is that the exact way to compute the area underneath the curve is really not by using 20 rectangles or not by using 40 rectangles, but we have to use an infinite number of rectangles. So that's the place where we're headed here. So this is a pretty important definition, but we're immediately going to get rid of this notation. But I like to spend a little bit of time talking about the ins and outs of this equation. So this is the idea of how you can calculate a bounded area. So any net area where the function may dip below the x-axis, it may stay above the x-axis, or it may be entirely below the x-axis. This is the way that you can calculate not an approximate area, but the exact area. So the different characteristics of this formula are important to see, because some of this is old stuff that we already talked about. So this here is the height of the function, right? F evaluated at a point, and then we have the width that shows up here. So it should make sense that when you calculate the area of a rectangle, you have a height times a width. And then something we talked about in the previous lesson is you have to look at the number of rectangles that you're using to approximate. So if you're adding up n of these rectangles, then you sum them up and you're going to have a good approximation for the area underneath the curve. So the reason this formula here will now give us not an approximation but the exact net area is simply because of this limit that's out in front. So when we think about the diagrams that we saw in some of the previous lessons, what you have to do is you have to use an infinite number of rectangles. So you have to let n go to infinity, and then what's really going to happen is the approximate area underneath the curve becomes the exact area under the curve. So here we're saying let n, right, go to infinity, and n here is the number of rectangles. So the only way you can conceivably calculate the exact area underneath the curve is to use an infinite number of those. So a big thing that we learn in this lesson is we're going to relax this notation. This is a very cumbersome notation because you have the height and the width, the summation there, and then also the limit out in front. So we're going to use a different notation for the same thing. Right, so for net area, this is going to be our new popular notation, and if you flip through the calculus book, you'll see this everywhere there in the text. So what we're saying is that this notation we're now going to replace with something a bit more meaningful, and definitely something that's simpler. So what I'm going to do here is to sketch a diagram, and we can see exactly where all the bits and pieces here come from. So we could have a function that does this kind of thing. Right, so some function there, and we're going to trap it on the left at A and trap it on the right at B. And then this is what we're trying to do, is to calculate this exact area underneath the curve. So this is going to be our new way of notating it, right? So this little symbol here is called the definite integral because it's calculating the exact area underneath the curve. So we write it just as we see here. So it's this definite integral from a to b, and it's f of x dx. So if you look at the characteristics here, a lot of this speaks exactly to this picture because you can see that this is the height that we're talking about, the function, and then dx we interpret very similarly to as delta x. So this here is going to be the width of the rectangle. So if you were to just draw one of these rectangles here to visualize what's happening, you can see that this rectangle here has a height of y, or f of x, and then the little width here, we would call this delta x. So all we're doing is we're really summing up the areas of all of these rectangles. And then our lower limit of integration is a, and it corresponds to the leftmost point, and the upper limit of integration is b, corresponding to the rightmost point. So you can see all of this here captures all the characteristics of what we're trying to do. And then the symbolism here calculates the net area, or in this case, if the function is above the x-axis, it's the exact area underneath the curve. Alright, so we're going to hit some odds and ends here, some basic results that come directly from this. This is a pretty significant theorem here in calculus. And so this one here is just saying, when is integration possible? So when can we go through and talk about the symbolism of the definite integral and go through and find the area underneath the curve? And so this result simply says, as long as the function is continuous on the window from a to b, then that means we can integrate it. Right? Then we could calculate the area underneath the curve. And it's very simple to just think about a diagram similar to the previous picture. So you have a function that does something like this, nice and continuous with no gaps. And so you can decide where to draw the a and the b as long as it's continuous there. And then this result is saying as long as you have continuity, then this area here, this enclosed area, will be well defined, and that means that you can go through and calculate that. So what I'd like to do here is to get a little bit of practice doing this and understanding what it means. So we'll go through a couple of simple calculation problems, and these are all about net area. So we have a two-part problem here. We're just going to use geometry to calculate these. So you can see we're using this notation immediately here to indicate the net area, or the area underneath the curve. Alright, so let's look at problem A. So this is saying the lower limit is 1 and the upper limit is 2. Notice the function here is x. So if we think of problem A, our function, the thing that we're integrating, f of x, is equal to x. Alright, so we're looking at this part right here. And so what we can do to figure this out is to draw a picture. I'm going to draw a little diagram here. So y equals x is a pretty simple one to sketch. Put that right in here. And then according to our problem, we're going to start to draw a vertical line at 1 and then also one at 2. So I'm going to put a little line here. So this will be at 1, and then we'll draw another one here at 2, just like that. And so this symbolism is just saying calculate this area. Right? Go through and compute that. So because this is a nice simple line, y equals x, we could say this is going to hit 1 there, and then right here it's going to hit 2, y equals 2. So if you want to calculate the area, naturally you can use the formula for the area of a trapezoid, but it's probably easier just to break this into a couple of pieces. So this is a square underneath here, a 1 by 1 square. So the area there is 1, and then this is clearly half of that, right, 1/2. So it turns out the area, right, from 1 to 2 would be 1 plus 1/2, right, just 1.5. So this is all just based on the geometry of the figure and then also just drawing a picture, right, getting it right from the diagram. So the one thing you guys should get accustomed to doing is writing this, right? When you integrate from 1 to 2, x dx, right, it indicates some kind of area underneath the curve, simultaneously above the x-axis, and this area happens to be 1.5. Right, so that's all there is to it. This is the calculation of the area of that. So B should be pretty similar. This one has different bounds, right? A lower limit of -2, an upper limit of 3. The function is slightly more complex. It's absolute value of x. So f of x here is absolute x. So we'll do the same thing, draw a diagram, and then just calculate the area from geometric figures. Right, so the absolute value is that v-shaped function. So it looks like y equals x here. Looks like y equals -x there. And so this problem is saying let's go from -2 to +3. So I'm going to back up 2 and draw a little line here to enclose that. And then we're going to go forward 3 right here. We'll draw another line here. Right, so the enclosed area here, we could see we have a right triangle there, and we also have a right triangle here. So if you want to calculate the value of this definite integral, it simply means calculating those two areas and just adding them up. So this one looks like it won't be too hard. So this will be a 2 by 2 right triangle, right? So 1/2 base times the height. So 2 times 2 will be 4. If you cut that in half, you're going to get 2. So that's the area that we get over here. And this will be a 3 by 3. So we'll have to take 9 and cut it in half. So you could just say 9/2 or 4.5. So you could simply add these up, 4/2 plus 9/2, you're going to have 13/2. So the value for this one here, so if we say let's integrate from -2 to 3, absolute value of x dx, right, this is going to equal just the sum of these two. 13/2 is the area. So realize here, out of pure convenience, these two problems, right, once you understand the meaning, the area underneath the curve, happen to be very, very easy because the objects that you see in front of you happen to be very convenient geometric objects. So in the event that these functions bent in some way and you had an irregular shape, then you might have to go back to using the sums, right, and approximation. Alright, so last thing I want to talk about are some different properties of the definite integral. So there are 5 altogether. I'll write the 5 of them down and then we'll talk about an interpretation of each one of them. Okay, so we could go through some of these, I think, pretty fast. So these are just some properties. So the first one here, a little different looking. You might need to think about this one. Okay, so this is property number 1. So this is saying we're finding a definite integral, but we're integrating from a to a. So there's literally no movement in the horizontal direction, and this says that the calculation of the area ends up being 0. So one way of convincing yourself of this is just to draw a diagram of this. So you have some kind of function here, and then what it's saying is the lower limit and the upper limit are identical. So if you think about this for a minute, you can think about a little vertical line like A, and then what we usually do is we move to the right to enclose some two-dimensional figure, but in this case the starting point and the ending point are the same, so literally the object you have is a one-dimensional thing. So you have a line segment, and so the area of something one-dimensional is going to be 0. Right? So our interpretation of area here is you don't actually have anything in 2 dimensions, so it must calculate to 0. So the second one here, we could say there's a little bit of geometry going on with this one. So this one I tend not to talk about too much, but it's good to mention. So this is saying we're going to integrate from a to b. So what we could do is to switch the order, right, of the limits of integration. And all that does is affect the sign. So this is saying conventionally a is less than b. So if we want to find the area underneath the curve from a to b, in theory we could switch directions and integrate from b to a. So this is the thing that has changed here. So that would put everything on its head with respect to the coordinate system. So the way we adjust that, right, is we put a negative sign out in front. So this is yet another property of definite integrals. Right, so I'll keep on numbering these as we go through them. So number 3 has a nice geometric interpretation. So this one here I'll write out because this one looks a little bit long. So this one is saying we are again going to integrate from a to b. So this one here we need to carefully study. Probably the longest one of the 5 that we talk about. So it's saying if you want to find the area underneath the curve for a definite integral from a to b, then what you could do is you could integrate from a to c, right, and pause for a minute, and then finish the job, go from c to b. So this one has a nice little diagram that can accompany. So on the left-hand side here, right, we could say what we're trying to do is to find this area bounded underneath the function f, but going from a to b. And so on the right-hand side it says we can integrate from a to c. So most people visualize this as putting c somewhere in between a and b. That's definitely a very good geometric way of thinking about it. So just this integral here, right, from a to c would correspond to this area. And then it says what you could do is you can add to that the integral from c to b. So if you look at going from c to b, that's going to give you this little portion here. So it should make sense if you look at the right-hand side that if you sum these two up, when you add them together, you get exactly this integral here from a to b. So it's simply saying you can divide your work into parts, and as long as all of the parts add up to the original integral, then geometrically that's a perfectly sensible thing to do. Alright, and then we just have the last two. These should look familiar because we've talked about these already when we discussed antiderivatives. So number 4 has this form here. So this is saying if we're integrating from a to b a constant multiple of a function, then what we could do is to pull the constant out in front. So we could put the k here, then integrate from a to b f of x dx. So this is something that we mentally do with anti-differentiation. So when you have a multiple of a function, we treat the multiple as an important piece of it, but ultimately the multiple ends up as showing up in your answer as part of the answer. So the k can be removed outside of the definite integral, and then you can just worry about the area underneath the curve. Alright, and then we have the last one here. This one I might also have to write on a couple of lines. So this tells us how we can integrate sums or differences. So I'll write it, I guess, for the sum. So let's go from a to b. Let's say f of x plus g of x dx. So this is saying if we have a couple of functions, f and g, we're adding or subtracting them together and finding the definite integral, so the area underneath the curve. It's really telling us that we can divide the labor. So we could integrate the f and then integrate the g. So we could just do a to b f of x dx, and then you can add to that the result a to b g of x dx. And this is something that we mentally do, right, when we do these calculations, but we're making it explicit in these properties. So on the right-hand side of property 5, it's really just one integral that we're talking about. So we're integrating the f plus g, but what we can do is to split this up into the area under the f function, and then the area under the g function, and then we can take those two results and simply add them up. So these properties 1 through 5 we'll use in a variety of ways when we're talking about definite integrals, any kind of net area or area underneath the curve.